Hi everybody. Today's video explores the different forms that quadratic function equations can take. And so as you see here, we have a picture of four parabolas, right? So they must be the graphs of quadratic functions. First thing we might want to take a look at these things and ask ourselves is whether these parabolas, these nice parabolic shapes, actually take the exact form that we would expect a parabola to take. We've explored, using a table of values perhaps, that parabola will will follow the shape of, starting at the vertex 1 over 1 up, right, in both directions. It'll be 2 over and 4 up, 2 over and 4 up, 3 over and 9 up, etc. And I think each of these parabolas, when we look at it, yeah, it looks like it. It seems like these ones follow exactly what we'd expect to, 1 over and 1 up, 2 over 4 up, etc. So looks like the parabolas we have listed here, kind of labeled C, D, E, and F, they all follow the basic parabolic shape. We have noted that parabolas can be a little bit stretched, might look a little bit skinnier. They can also be squished down. They might look a little wider. Looks like these ones are pretty standard. And so the question is asked, for which of these graphs do we know the function equation? And I think by now, I'm hoping that most of you would know that the equation for C, being the simplest parabola of all, would be just the simplest equation of all, y equals x squared, right? If you filled out a table of values for that, you would see that the points would all be 1, 1, negative 1, 1, 2, 4, negative 2, 4, etc., 3, 9, and it would fit exactly. In our quadratic equations unit, we started graphing parabolas based on knowing x-intercepts, and this guy here has two x-intercepts. In fact, he seems to have two kind of nice x-intercepts. We see one here at 1, 0, and we see one here at 5, 0. And based on our quadratic equations units, where you looked at these before, you might guess that the quadratic function of this parabola, the one that goes through 1 and 5, would have something like y equals x minus 1 and x minus 5, right? And if you actually solved that for x-intercepts, you'd say, yep, those x-intercepts match up exactly. Also in our quadratic equations units, we looked at parabolas that had just one x-intercept, this one x-intercept right here at 3, 0, and I would expect you to say, well, that D graph, that's just a perfect square because it has 1, and it's probably something like this. But this parabola that's kind of floating in midair, no x-intercepts, we've only recently maybe taken a little bit of look at how could we actually name this thing. Now again, remembering that this thing has the standard form, so we don't have to worry about too much. We just have to really talk about where this guy is, right? And so the question is, what is the quadratic function equation for this parabola at E? And perhaps you've seen something like this before, and you say, well, the one that's at E is just like the one that's at D. It's got a vertex on the same axis. It's just raised up 4 from that. And maybe you recognize this function equation. Maybe you've seen something like it or something like this form before. Now the question is asked, in how many forms can the function equation for f be expressed? And I would say that you could express the equation for f in 3 forms. Number 1, factored form. Number 2, standard form. And number 3, vertex form. Factored form we already looked at. We said this one was easily expressed as x minus 1 and x minus 5. Standard form is easily obtained. We obtain that by actually foiling out or expanding and collecting terms of whatever we have from factored form. So if we foiled out what we have here with the x minus 1 and the x minus 5, I think we would get x squared minus 5 minus 6 is minus 6 plus 5. So that would be what standard form looks like for function f. And vertex form would be in the form that we just showed for E. It shows, part of it shows where is the axis of symmetry. Now you'll notice that the sign on the number is a little bit different, but this thing definitely goes through an x value of 3, and it's going through an x value of -4, right? And we saw that this relates exactly to a vertex of 3, -4. You'll notice there's a relationship between what's here and what's here in the vertex. But this sign here is always opposite in the vertex. This sign, it stays the same. So, the three forms, factored form, standard form, and vertex form. We write these often in some general kind of form. And for example, factored form being in the form y equals x minus r and x minus s. And of course, if you've been paying attention, that this form tells where our x-intercepts are, right? Usually there's numbers here where the r is and the s is. So generally speaking, we would say that the x-intercepts are then at, I guess, r0 and at s0. Standard form, you've seen before, y equals x squared plus bx plus c, right? You recognize this is the form we use when we're solving quadratic equations. And among other things, this one always tells us the y-intercept. Right, you recall that when you find x-intercepts, you let y equal 0. Well, if you want to find a y-intercept, you let x be 0. And in this equation, if you let this x be 0 and this x be 0, it wipes out the entire equation and tells you that the y-intercept must be that y equals c. And so, quite simply, the y-intercept will then be at 0, c. Now, vertex form is generally written as x minus h squared plus k. I didn't pick these letters, by the way. They're generally used. They're used by your textbook, for example. And of course, vertex form is aptly named because it tells us, of all things, the vertex, right? And I usually label it with a V, reminding you that, and this will mess all of us up at some point, but it's the opposite sign of whatever this is. So if it's negative h here, it's going to be positive h there, but if it's positive k here, it'll stay positive there. So the sign changes for what's ever here to there, sign stays the same there, and so if we just fill in what we got, it'll be just h and k will be the location of our vertex. So a couple things about this. Number one, it is possible, like we saw in the previous example for f, that the same parabola, the same quadratic function could be expressed in all three forms. And the way that you see them here, that's exactly how they would be with numbers in them, of course. For a quadratic function, that's kind of the standard 1 over 1 up, 2 over 4 up kind of shape. As you've seen before, there can be some stretchy parabolas that look pretty skinny or some squished parabolas that look pretty wide, and they would have some kind of number in front. Okay, they would have some kind of a value in each of these equations. There's a spot for an a value. And among other things, we call that a value the stretch value, the vertical stretch factor. Now, if you were using the same parabola for all three equations, then the a value would be the exact same for all three of them, because just describing them as one equation or another does not change how stretched they are or how squished they are. Now, we'll get to these parabolas in a minute, but these are worth looking at because they're good examples of parabolas that are stretched or squished a little bit. They have a stretch factor. For example, this parabola here, this D parabola, if you looked at this and said, hey, does this, starting at the vertex, does this go 1 over and 1 up, 1 over and 1 up? No, it doesn't. In fact, it goes 1 over and 2 up, right? Does it go 2 over and 4, 1, 2, 3, 4 up? No, in fact, it goes 2 over and 8 up, right? And so in both of these cases, right? 1 over and 2 up, that's twice as high as we would expect. 2 over and 8 up, that's also twice as high as we would expect. And I bet if I went 3 over, I would see that this thing goes 18 up instead of 9. And we would say that this guy has a stretch factor A of 2. Everything's twice as tall as we expected it to be. If we look closely at this E parabola, then we say, well, let's see, from here, 1 over and 1, 2, 3 down. That's 3 times as much as we'd expect. We'd expect it to be 1 over and 1 down, but it's 1 over and 3 down. Let's just see, 2 over and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I think. We were expecting 2 over and about 4 down, or exactly 4 down, but it was 2 over and 12 down. So that tells me that this thing is stretched 3 times as much as I had expected. And so this one would have an A value of 3 that I could just plunk into the equation. How about this guy C over here? What's going on with him? Well, let's see. Instead of going 1 over and 1 up, this guy goes 1 over and about half up. When we go 2 over, we expect to go 4 up, but it only goes 2 up. Looks like this guy is only about as half as tall as we was expected. I can check that. Let's see, if I go 1, 2, 3, 4 over, I expect to go 4 over and 16 up the square of 4, but if this thing is only half as tall as we expect, it should only be 8 high. 1, 2, 3, 4, 5, 6, 7, yes, 8 tall all the way to here. This guy is actually squished together to be half as tall as we expect. So we would put an A value of 1/2 on this guy. So we'll get back to those in a minute, but that's how you would be looking at something that would have an A value instead of a blank. Now, if we leave it blank, that means that there is an A value. It's just of 1, and doesn't even have to be written in. So let's work through a couple of examples and see how many forms we can come up with for each of these quadratic functions, each of these parabolas. That D parabola, I think you would be able to look at that and say, oh, it's a 1-intercept parabola. The vertex is right on the intercept. Looks like this thing is just written as a perfect square trinomial, right? X-intercept at 2. And so if we were to come up with a factored form, this is what it would look like. If you wanted to convert that to standard form is easy. Factored to standard form is just expand and collect, right? So FOIL it out, and factored form then would be the expanded version of that, x squared plus 4x plus 4. And the vertex form, well, the vertex is at -2, 0, so it'd be x plus 2 squared, and I guess plus 0. Now, we probably wouldn't write in the plus 0, but you can see that that would go there. Is there an A value besides 1 that belongs in any of these spots? Well, no, this is the standard kind of shape, right? 1 over 1 up, 2 over 4 up, right? That's pretty easy to take a look at. So we don't have to add anything in front for an A value. How about E here? E looks like it has a vertex over here of 5 and 9. It also looks like it has nice x-intercepts here at 2 and at 8. So maybe that's a nice place to start, E. We would say, well, in factored form, x minus 2 and x minus 8 would be the factors for factored form. What's missing from this? Well, we know that this is a parabola that opens down, right? So we know it's upside down. It needs negative in the A spot, a -1 if you will. We don't have to write in the 1 part, but that's what gets written in. So standard form again, just by foiling it out, probably maybe in 2 steps, x squared minus 10x plus 16. So I would write it as y equals -x squared plus 10x minus 16. And of course that would be standard form. Vertex form, well, since I know the vertex is at 5, 9, I remember, okay, well, vertex form is x opposite sign minus 5, same sign, plus 9, right? That would give me a vertex at 5, 9, and so vertex form, again, remembering that since this thing opens down, it needs to have a negative in the A spot to show that it's upside down. So now looking at this third parabola, f, we still notice that it's not especially stretchy, right? 1 over 1 up, 2 over 4 up. This is has an A value of 1. It opens up. It's positive. Looking at these x-intercepts, they don't look particularly pretty, right? They don't go through exactly anywhere. That probably tells us that this thing does not have a nice factored form, right? A factored form always tells us exact x-intercepts, and if it doesn't have exact x-intercepts, there's probably not a nice factored form, not one that would be interested in exploring anyway. So I think for f, we're just going to look for two forms, right? The two easiest forms. I don't think we can start with standard form, but I think we can figure out from vertex form. In fact, why don't you take a guess and write down what you think the vertex form of f should be, and then use that vertex form and see if you can FOIL it out, collect your terms, and come up with a standard form for that. So press pause and give that a try. Since it looks like this thing has a vertex at -4, -5, then when I fill in vertex form, it must be opposite sign, x plus 4, same sign, -5. Now, if I need standard form for this, I'm just going to FOIL that out. So y equals x squared plus 8x plus 16 minus 5. Therefore, y equals x squared plus 8x plus 11, it looks like. And this would be vertex form, and this would be standard form. And of course, I'm always interested in seeing if what I come up with my equation agrees with what I have in my graph. And in each of these cases, I could take a look and see, hey, there's a plus 11 here. I said that would be my y-intercept. Let's see. Oh yeah, that matches up, right? This one here, -16, not actually on this graph, but we could make an argument that that looks like it would be heading towards -16, right? So that's a little bit of a handy thing in standard form. If your graph matches with the y-intercept right here, then we know we're on the right track with our standard equation. And so, looking at this last collection of parabolas, C, D, E, and F, I suppose it would have been smart to name them different letters, but there you go. I hope you recall looking at these and saying, for example, for D, when we looked at it, it went 1 over and not 1 up. It went 1 over and 2 up, right? It went not over 2 and 4 up. It went over 2 and 8 up, right? And that told us since everything was twice as high as we expected it to be, it has a stretch factor of 2. So the A value for this one was 2. So take a minute, see if you can figure out some stretch factors for C, for E, and for F. Just press pause for a second. I think in C, everything is half as high as you expect it to be. So I think that A is a half for C. I think in E, everything is 3 times as tall as you expected it to be. It's 1 over and 3 down, looks like. So, but it is upside down. So that tells me two things, that A must be a negative for E, and it must be 3, -3. In F, looks like that one looks pretty wide, but it's actually wide because it's squished down. And so how does it go? It's kind of hard to tell 1 over and who knows how far. We were expecting 1 up, but it went 1 over and much less than that. It goes 2 over, and we were expecting 1, 2, 3, 4, but it only goes up 1, right? 2 over and 1 up. If we were expecting 4 and we only got 1, to me that tells me that this thing is 1/4 as tall as we expected it to be. Maybe you check out what happens when you go, for example, 4 wide. We're expecting 16 tall. How tall is this one? Now, I don't believe that C, E, or F have a nice factored form. I know for sure that C doesn't have a factored form at all. It doesn't have any x-intercepts. There aren't going to be any factors. E and F, they do have 2 x-intercepts, but I do not think that they are very nice x-intercepts. I'm guessing that I'm just going to, for most of these, for C, E, and F especially, I'm just going to be able to find or come up with a vertex form, and I'm going to use that vertex form to find a factored form. So for each of these examples, you should find the vertex form for each, and then you will have to FOIL that out, expand it, collect your terms to find standard form. Don't forget to include the A value in your vertex form, and then to, after you're done foiling, distribute that A value into the standard form. You should try each one of these on your own. I will, in the next slide, include a worked-through example of how I would do F. For answers for D, C, and E, you can refer to the link that's provided on EDSB. So looking at the parabola for E, we see the vertex is at 5, 9. We also see that this thing is stretched vertically by a factor of 3, and it's upside down, so hence the negative and the 3 for the A value. And so I would guess that y equals x minus 5, opposite sign, squared, plus 9 with a negative 3 in the front here. And so that would of course be vertex form. And in order to get to standard form, I would just expand, right? Y equals, I would leave my negative 3, I would expand the x minus 5, distribute the negative 3, negative 3x squared plus 30x minus 75 plus 9, and then finally y equals negative 3x squared plus 30x minus, I guess it would be 66. Right? Now I don't have a y-intercept on my graph to compare that to, but I think that's correct. So check your answers for the other one. Big lesson for today, but very, very important that you know the 3 forms of quadratic function equations: vertex form, standard form, and factored form.